There's a walk you can't take. Not because it's dangerous, not because it's far, because it's mathematically impossible, and a guy proved that without ever putting on his shoes. Picture an old city split by a river, two big banks, two islands in the middle, and seven bridges stitching the whole thing together. On a Sunday afternoon, people there had a little game. Try to walk through town, cross every single bridge, but cross each one exactly once. No repeats, no cheating and swimming. Just a stroll that hits all seven and doesn't double back over any of them. Sounds easy, right? Sounds like the kind of thing you'd solve by being a little clever, maybe starting from the right spot. So people tried. They tried a lot. Nobody could do it. And here's the part that gets me. For a while, everyone assumed that just meant they weren't clever enough yet, that the right path was out there and somebody would stumble onto it. Watch the blue dot. It's going to try, and it's going to fail, and the failing is the whole point. Because the answer isn't hidden. The answer is that there is no answer. And figuring out why is where an entire branch of math gets born. Let me actually introduce the place, because the geography matters for about 2 minutes, and then it stops mattering completely, which is the fun twist later. This is Königsberg, an old Prussian city. There's a river called the Pregel running through it, and the river does this thing where it forks and wraps around an island right in the middle of town. So you end up with 4 chunks of land, the north bank up top, the south bank down bottom, a big island in the center, and a smaller sliver of land off to the side, where the river branches rejoin, 4 pieces, and connecting them, 7 bridges, each with its own name, some of them genuinely charming, like the Honey Bridge and the Green Bridge. The central island alone touches 5 of the 7. It's the busy hub of the whole thing. Now the townspeople's puzzle was this walk I told you about. Cross all 7, each exactly once, and you're allowed to start and end wherever you like. That freedom to start anywhere feels like it should help. More options, easier problem. Keep that feeling in your head, because Euler is going to take that freedom and turn it into the exact thing that dooms you. Watch how many bridges touch that middle island. Count them with me. 1, 2, 3, 4, 5. Enter Leonhard Euler, Swiss mathematician, absolute machine. Probably wrote more math than anyone who's ever lived. In 1736, this puzzle lands on his desk, and honestly, at first, he's a little dismissive. He writes to a friend that it seems trivial and not really mathematics, more of a geography thing, a riddle, and I love that, because it's the exact reaction you'd have. It doesn't look like math. There's no equation. There's no number to solve for. It's just a map and a walk. But Euler keeps poking at it, and he realizes something that flips the whole problem sideways. The specific shape of the island doesn't matter. How long each bridge is doesn't matter. The river's curves, the distances, the angles, none of it. The only thing that decides whether the walk exists is which land connects to which, and by how many bridges. That's it. That's the entire soul of the problem. Everything else is decoration. And once you believe that, you're allowed to do something that felt illegal at the time. You get to throw the map away. Take the pretty picture and crumple it up. We're going to redraw this city as something so stripped down it barely looks like a city at all. And that stripped down picture is the first graph anyone ever drew. Okay, watch this part. This is my favorite move in all of math. Each piece of land we're going to squash down into a single dot. Doesn't matter that the island is big and the sliver is small. A dot is a dot, so 4 dots. North, south, the big island, the sliver. And every bridge becomes a single line connecting 2 dots. 7 bridges, 7 lines. That's the whole city now. 4 dots, 7 lines. Let me place them. Big island in the middle. The other 3 land pieces around it. Now I draw the connections. The island connects to the north bank with 2 separate bridges, so that's 2 separate lines. 2 to the south as well. 1 line over to the sliver. And then the sliver reaches up to the north bank and down to the south bank. Count the lines. 7. Every bridge is accounted for, and nothing about the geography survived except the connections. This little picture has a name now. The dots are called vertices, and the lines are called edges. Ugly words, I know. Mathematicians are not great at branding. But this object, vertices and edges, is a graph. Not a graph like a bar chart. A graph like a web of relationships. And you just watched one get invented. Now the graph just sits there looking innocent, but it's hiding the answer, and the key is to count. For each dot, count how many lines touch it. That number has a name too, the degree of the vertex. The big island, in the middle, 5 lines touch it, degree 5. The north bank, 3 lines, degree 3. South bank, 3. And the little sliver, 3 as well. So our 4 degrees are 5, 3, 3, 3. Hang on to those numbers. We're about to squeeze the entire impossibility out of them. Here's the intuition, and I got this wrong the first time I thought about it. So if it takes a second, you're in good company. Think about any dot that is not where you start and not where you end. A dot in the middle of your journey. Every time your walk enters that dot across one bridge, it has to leave across a different bridge, in and out. Enter, exit. The bridges get used in pairs at that dot, which means for any land you're just passing through, the number of bridges touching it has to be even. It has to pair up perfectly. One to come in, one to go out, over and over. An odd number leaves a bridge stranded with no partner. So passing through a piece of land forces an even count, even degree, but your start and your end are special. When you start somewhere, your first move is to leave, one bridge out with no matching in before it. And when you finish somewhere, your last move is to arrive, one bridge in with no out after. So the start and the end are allowed to have an odd degree. They get to be the exceptions. Now count the exceptions you're allowed. You start in exactly one place, you end in exactly one place. That's at most 2 spots that can carry an odd number of bridges. Everywhere else even, no arguing. So here's the rule. Euler squeezes out of the whole thing, and it's shockingly small for how much it decides. A walk that crosses every bridge exactly once can exist only if the number of odd vertices is 0 or 2. 0 if you loop back to where you started. 2 if you start one place and end another. 3 odd vertices, 4. Forget it. Impossible before you take a single step. That's it. That's the master key. One count. Now let's take that key back to Königsberg and watch the door refuse to open. Back to our 4 dots. Their degrees were 5, 3, 3, 3. Now the only question that matters, how many of those are odd? 5 is odd. 3 is odd. 3 is odd. 3 is odd. Every single one. All 4 vertices are odd. And the rule said you're allowed at most 2. We've got 4. So the Sunday walk is not hard. It's not waiting for a smarter person. It flat out cannot exist. And now you can prove it in about 10 seconds to anyone. At a party, on a napkin. That's the thing that still amazes me about this. For years people treated it as a puzzle you might crack with enough patience, and the real answer was that patience was never going to matter, because the obstruction is baked into the connections themselves. Euler didn't find a clever route. He proved no route is possible, and proving something can't be done is a totally different kind of victory. It's calmer, it's more final. Nobody's ever going to email you saying, actually, I found a way, because you can hand them the count, and the count doesn't budge. 4 odd dots, doors locked. Always was. Let's play, because a rule you can only apply once is boring, and this one you can apply to everything. Take a square, 4 corners, 4 edges around the outside. Every corner has 2 edges, degree 2, all even, 0 odd vertices, so you can trace a square in one stroke without lifting your pen and end up back where you started. Try it. It works. Now add 1 diagonal. The 2 corners, the diagonal touches jump to degree 3, odd. 2 odd vertices, exactly. Still legal, but now you can't return to start. You have to begin at 1 odd corner and finish at the other. And here's the classic, the envelope. That little house with an X shape kids draw in 1 line. Count its odd corners and you'll find exactly 2, which is why it works, and why you always have to start at the bottom corners and never the top. It was never about being good at drawing. You were unconsciously obeying Euler the whole time. Same rule every time. Even everywhere means loop. Exactly 2 odds means a path between them. Anything else, your pen is going to have to cheat. So 1 impossible walk, fine, cute. But the reason this shows up in every math class now is what Euler quietly did to the idea of a map. He said the distances don't matter, the shapes don't matter, only the connections matter. That sounds small, and it is enormous, because the second you believe it, all sorts of things that look totally different turn out to be the same object. A subway map. You don't care that the train curves are how many meters between stops. You care which station connects to which. That's a graph. Your group chat. People are dots. Messages are edges. Graph. The internet. Links between pages. Molecules. atoms bonded to atoms, airline routes. Who's friends with who on any app you've ever used? That little people you may know box. That is somebody running graph algorithms on a giant version of this exact picture. All of it descends from a guy staring at 4 dots and 7 lines and deciding the geometry was noise. This field even has a name now, graph theory, and a close cousin called topology, the math of what stays true when you bend and stretch everything. Same DNA. Distances are a distraction. Connection is the truth. Okay, here's a question that bugged me until I actually did it. What if we cheat the map itself? The walk is impossible because 4 dots are odd, but odd and even aren't fixed by fate. They depend on the bridges, and bridges are things humans can build. So what's the smallest change that fixes Königsberg? Watch. We've got 4 odd vertices. We need to get down to 2 or 0. Every new bridge we add flips the parity of the 2 lands it connects. Odd becomes even. Even becomes odd. So if I build one clever bridge between 2 of the odd lands, say connect the north bank straight to the south bank, both of them flip from odd to even. Just like that, we go from 4 odd vertices to 2. And 2 is legal. Suddenly the walk exists. Add that single bridge and the impossible Sunday stroll becomes a Sunday stroll. One line, and honestly there's a real world epilogue here. Königsberg is now Kaliningrad. The map changed over the centuries. Some bridges were destroyed in the war, some rebuilt. And depending on which year you check, the walk has actually flickered between possible and impossible. The math didn't change, the bridges did. Let me close the loop on Euler himself, because the rule I gave you is only half of what he proved, and the other half is the satisfying part. I told you if a walk exists, the odd count has to be 0 or 2. That's the necessary direction, it rules things out. But Euler also argued the reverse. If your graph is all connected in one piece, and the odd count is 0 or 2, then a walk really does exist. It's not just allowed, it's guaranteed. You can always find it. So the count isn't just a bouncer turning people away, it's a promise. 0 or 2, odd connected graph. Go ahead, the path is there waiting. That two-way street is why we still name these things after him. A walk that uses every edge exactly once is called an Eulerian path, and if it loops back to start, an Eulerian circuit. His name stuck to the idea almost 300 years later, and the wild thing is, he thought this problem was barely mathematics. He solved it almost as a favor, a little diversion, and accidentally opened a door that people are still walking through, building GPS routing and network design, and who knows what next, on top of 4 dots and 7 lines. So here's where I leave you, and it's not a neat bow, it's the thread that still tugs at me. Euler's rule is about crossing every edge exactly once, every bridge, but there's a sister question that sounds almost identical and is a completely different beast. What if instead of every bridge you want to visit every dot exactly once, every piece of land once, and you don't care about the bridges you skip? Feels like the same flavor of puzzle, right? Same graph, tiny change to the goal. It is not the same. That version is called a Hamiltonian path, and unlike Euler's, there is no nice little count that tells you whether one exists. None. For a big graph, the fastest known way to be sure is essentially to try paths and hope, and this innocent-looking cousin is tangled up with the biggest unsolved problem in computer science, the P versus NP question, a literal $1,000,000 prize. Same dots, same lines. One version Euler cracked over a weekend in 1736. The other one has humbled everyone who's touched it for decades. And I don't have a tidy reason why one is easy and one is monstrous. Nobody does. That's the part that still bugs me, and I kind of love that it does.